can be a barren realm. With increasing depth, we find an exponential decline in biomass, which has driven creatures of the deep to adapt in weird and wonderful ways. Generally, these organisms must rely on marine snow as a source of food. A trickle of fecal pellets and dead organic material that drifts downwards from the surface waters, where photosynthetic primary productivity is possible. Below 200 meters, levels of ambient light from the sun are too low for photosynthesis to occur, and at around 1,000 meters, aside from the infrequent twinkling of bioluminescence, the ocean is drowned in pure darkness. Without photosynthesis, the supply of scraps are all that remain to nourish any life. However, on the deep sea floor, there are important regions where primary production is possible via a different mechanism called chemosynthesis. These are the chemosynthetic oases of the deep sea, which represent some of the only locations on Earth where the ultimate source of energy for life is not sunlight, but the Earth itself. In this series of films, we'll delve into their formation and ecology, as well as the threats they face, and the importance of stewardship for these fascinating environments. The process of chemosynthesis is similar to photosynthesis. Both can be defined as the creation of organic matter from the fixation of inorganic carbon using energy. But what differs is the source of that energy. In parts of the deep sea, primary production is fueled by chemical energy, rather than energy from the sun. But this can only take place at certain seafloor environments, where the required chemicals are released into the water. The two main examples of such environments are hydrothermal vents and cold seeps. The former were only discovered in 1977 when scientists were exploring an oceanic spreading ridge near the Galapagos Islands. What they discovered was a hidden world that revolutionized our understanding of how and where life on Earth can exist. Since then, hundreds more vent fields have been discovered, often at depths of 2 kilometers or more, along Earth's convergent plate boundaries and at seafloor spreading regions where the oceanic crust is moving apart. One major site of high vent abundance is the East Pacific Rise, where the fast spreading rates have created vent fields dotted along the ridge, tens of kilometers apart. In contrast, the vent fields of the much slower spreading mid-Atlantic ridge may be hundreds of kilometers apart. They form here because the rifting of tectonic plates creates fissures in the crust and allows hot magma from deep within the Earth to rise closer to the seabed. Upper parts of the sea floor are very permeable. Cold seawater enters and percolates down through the crust where it becomes superheated and takes up minerals from the surrounding rocks. This mineral-rich fluid then jets back into the ocean at extremely high velocities and temperatures exceeding 400 degrees Celsius. As the fluids mix with cold seawater, the dissolved minerals precipitate out in smoke-like billows and build towering chimney structures on the sea floor. There are a few varieties of hydrothermal vent, characterized by the specific mineral content of the vent fluid. Black smokers emit the hottest, darkest plumes, forming chimneys over 50 meters tall, with high levels of sulfides that precipitate on contact with the cold ocean to form the black smoke. In contrast, white smokers contain barium, calcium, and silicon. Other vents may be characterized simply by shimmering streams of water. Although the throat of vent chimneys can reach around 400 degrees Celsius, there is a very sharp temperature gradient between the fluid and the surrounding seawater. Across a distance of around 10 centimeters, temperatures can drop from over 300 degrees to just 2 degrees Celsius. Most vent animals live at far cooler temperatures, but prokaryotic microbes, including forms of both archaea and bacteria, are able to tolerate fluids as hot as 122 degrees Celsius. Here, they carry out chemosynthesis via a number of different pathways that depend on the specific conditions of their microenvironment and the chemicals that are present. Typically, they use energy stored in the chemical bonds of hydrogen sulfide and methane to create glucose from water and dissolved carbon dioxide. The result of this chemosynthetic primary productivity is the presence of vast assemblages of animal life, concentrated at these regions. The supply of nutrients forms the basis of a food web for a diverse community of specialized organisms. An oasis of life in the deep. To understand just how significant these communities are, you only have to compare the life of hydrothermal vents with non-chemosynthetic deep-sea environments. Out on the abyssal plain, life is present but scattered. Animals must spread out in order to stand a chance of gaining enough nutrients from marine snow to sustain themselves. But at the vents, the chimneys are encased with dense colonies of rust-coloured snails, swarms of deep-sea shrimp, or expansive aggregations of ghostly white crabs competing for space on the rocks. Remarkably, these varied and abundant species are all sharing a single resource. They all rely on the chemosynthetic microbes as a source of food, meaning vents are sites of significant interspecific competition, that is, competition between members of different species. Often, interspecific competition can lead to the extinction of one or more of the species competing. The species that is less suitably adapted may lose out on the resources it requires and become out-competed. The idea that in a stable ecosystem, no two species can have exactly the same niche and stably coexist is known as the competitive exclusion principle. But when this doesn't lead to extinction, interspecific competition can instead cause specialization of the different animals. A phenomenon called resource partitioning occurs, where species with overlapping fundamental niches evolve different adaptations. It allows the species to coexist because there is less direct competition between them. This is what occurred at hydrothermal vents to make them so stable. The competing crabs, worms, and shrimps may all be in pursuit of the same resources, but they have developed very different ways of acquiring them. Squat lobsters and limpets graze the microbial mats that surround many of the chimneys. We also find suspension feeders like deep-sea mussels, feeding on free-living microbes that are suspended in the water. Yeti crabs farm the bacteria in filamentous hair-like colonies on their bodies, reducing the pressure on the crabs to compete for space with other species like shrimps. The crabs are able to move around and take the bacteria with them, with the microbes acting as epibionts inhabiting their surface. Giant tube worms are sessile, meaning they are fixed in one place and cannot move. Their competitive advantage arises from their ability to form an endosymbiotic relationship with the microbes. They store them within their tubes, effectively holding them captive and benefiting from the nutrients they produce. The worms take up hydrogen sulfide and other chemicals from the vent fluids in order to feed the bacteria. In return, the bacteria provide the carbon that the tube worms require in order to live. It is also thought that the bacteria benefit by being sheltered within the tube worms, and are therefore protected from predatory grazers like limpets and crabs. Another denizen of deep-sea vents, the Pompeii worm, farms bacterial colonies in a similar fashion to Yeti crabs, but its higher thermal tolerance allows it to inhabit locations on the vent structures that are far hotter than those that the crabs can endure. Here, they dwell within U-shaped tubes which can reach temperatures up to 80 degrees Celsius. Thus, much like we see with creatures of the rocky intertidal zone, there is zonation here between different animal species, which occurs due to the presence of a temperature gradient and varying abundances of different microbe varieties. In a way, the worms and crabs have become geographically isolated from one another within the same vent system. All the creatures we've discussed so far can be classed as primary consumers, but organisms from higher trophic levels are also present. The octopus, for example, is one of the top predators of deep-sea vents, along with white zoarchid fish, which feed on the tube worms and shrimps. Some deep-sea skates, which tend to dwell along the continental slope, visit hydrothermal vents to feed, but also to lay their eggs. They do so in order to use the volcanic heat to accelerate egg development and reduce the usually years-long incubation time. The zonation of life at vents leads to a higher abundance of filter feeders and predators in the periphery, further from the chimneys. Animals like stalked barnacles and predatory anemones are less tolerant of the chemical-rich, low-oxygen conditions found closer to the fluids, but they can still make a living here. Beyond the periphery, we find non-vent deep-sea fauna existing on the abyssal plain near the vent systems at higher abundances than they're typically found. This is because, even hundreds of meters away from the vent itself, animals can still make use of some of the exported organic matter. In all, over 590 animal species have been identified living at hydrothermal vents, and a surprising majority of these organisms are unique to this environment, having become specialized in such a way that means they rely entirely on the chemosynthetic conditions of the vents. The discovery of deep-sea hydrothermal vents was groundbreaking for another reason. Their unique conditions and the abundant nutrients of these chemical gardens led to scientists speculating whether these vents could be where life on Earth originated. Although unproven, there is substantial evidence to suggest this may be the case. Firstly, some of the thermophilic or heat-loving vent microbes are among the most primitive organisms known on Earth. Evidence is also given by the fact that many of the chemical building blocks of life are found at the vents, suggesting that the precursors of life harnessed carbon dioxide and hydrogen available in those primitive conditions to create complex organic molecules such as amino acids and nucleotides. In conclusion, hydrothermal vents support unique ecosystems and their communities of both highly specialized as well as simple organisms in the deep ocean. The islands of abundance they create in the otherwise barren depths are sites of outstanding scientific interest, providing a new insight into what is truly necessary for life to survive. But vents are not the only seafloor regions where primary productivity can occur. Along continental margins and down in oceanic trenches, we find cold seeps. Regions where cool, hydrocarbon-rich water escapes from the ocean floor and provides the necessary conditions for chemosynthetic assemblages to form. These mirror vent systems in a number of ways, but they give rise to an alternative set of conditions for life to adapt to and exploit. The geological origins of cold seeps differs from hydrothermal vents. While vents form from volcanic activity at seafloor spreading regions, cold seeps instead arise at the other end of oceanic plates, where they are subducted at the continental margin. Their formation begins with the burial of organic material under sediments on the sea floor. These organic compounds degrade over time, producing methane. Geological processes like the tectonic compression of sediments at subduction zones forces the methane from deep reservoirs up through the overlying sediments. Anaerobic microbes dwelling below the sediment surface oxidize this methane using sulfate, producing hydrogen sulfide and bicarbonate ions as a byproduct. This hydrogen sulfide, along with any residual methane, then serves as a vital energy source for chemosynthetic microbes. Thus, it is a consortium of two distinct sets of microbes that makes primary productivity possible at cold seeps, and lays the foundations of food webs here. The result is an environment remarkably similar to hydrothermal vents. We have a flux of sulfide and methane at the sea floor, chemosynthetic microbes using these compounds, and an abundance of life exploiting this productivity, fulfilling similar ecological niches and forming biodiversity hotspots in the deep sea. "70% of the Earth's surface is abyssal plain, a great, flat, sediment-covered region of the deep sea floor, characterized by low biodiversity due to the absence of primary productivity. But upon finding a cold seep, you're met with a sea floor region that's booming with life. Beds of Bathymodiolus mussels, endemic to chemosynthetic oases, encase the landscape. These animals seem to dominate chemosynthetic communities due to their ability to form an endosymbiotic association with the microbes. They host the bacteria within their gills and benefit directly from the food and energy they produce. The mussels also support other species, grazers like gastropods and orbinid polychaetes, as well as scavengers like shrimp and squat lobsters, picking at organic detritus produced by the mussels. Ciboglinid tube worms, belonging to the same family as the tube worms of hydrothermal vents, can be found here too. In a similar fashion to vent tube worms, they allow microbes to inhabit their internal trophosome, an organ specially adapted for housing chemosynthetic microbes. But one key difference between tube worms at vents and seeps arises from seep environments being soft sedimented rather than hard rock. Hydrothermal vents are located at mid-ocean ridges where sediment hasn't had time to accumulate on the newly formed oceanic crust. So the worms must obtain the sulfides from the water via their plume. In contrast, cold seep tube worms are able to burrow down into sediments and take up sulfide via their roots rather than just the plumes. They're even able to establish their extensive root system in the hard carbonate rocks that form at cold seeps. The continuous supply of sulfides sustains them for very long periods of time, allowing them to be slow growing. It's estimated that they may be able to live for over 200 years, forming tube worm bushes, which can contain hundreds of individual worms. Just like the mussel beds, these bushes create a complex 3D environment that supports a range of other organisms. Nestled among the cracks and crevices created by the mussel beds, we find another cold seep denizen you might recognize from hydrothermal vents. Although these yeti crabs are a different species to the ones at vents, they exhibit a similar trophic adaptation and farm colonies of bacteria on their bodies as epibionts inhabiting their surface. These crabs have developed long, hairy, claw-bearing arms, or chelae, which they wave directly in the sulfide-rich seepage. Predatory organisms such as octopuses, fish, and larger crabs are attracted to this vibrant community to complete the food chain. Incredibly, the abundant life of cold seeps significantly reduces the flux of methane from the sea floor to the water column, for organisms here represent the only biological methane sink in the ocean. This is called the benthic filter. At cold seeps with bacterial mats, it's thought that between 50 and 90% of released methane is consumed and taken out of the system. Since methane is a potent greenhouse gas which contributes to a warming climate, this consumption of methane by seafloor life has a major impact on regulating the global climate. Variations in the underlying geological processes can give rise to different types of cold seep environment, often with distinct communities adapted to the unique abiotic challenges. Types of cold seep include mud volcanoes, gas hydrate beds, asphalt seeps, and brine pools. Mud volcanoes form when methane gas and warm fluidized mud rise from over a kilometer beneath the sea floor, exploding out of the sediment in pulses. Over time, this builds up mud in the shape of a cone that protrudes from the sea floor and may be many kilometers wide. This is perhaps the most challenging cold seep variety for life to inhabit, as the soft, flowing mud makes it almost impossible for animals to settle. But along the borders of mud volcanoes, beyond the region prone to eruption, we occasionally find bacterial mats and meadows of tube worms thriving on the methane. Not all sites of methane seepage form mud volcanoes. Methane hydrate, sometimes called methane ice, is a frozen form of methane combined with water that forms in high-pressure, low-temperature conditions, meaning it's stable here at the deep sea floor, where it forms mounds. During their 2017 expedition in the Gulf of Mexico, NOAA's remotely operated vehicle encountered these gas hydrate mounds at depths of around 1,050 meters. On the outcrops themselves, the only macrofauna identified as living directly on the methane hydrate was a species of polychaete called ice worms. At only 2 to 4 centimeters long, these worms burrow into the hydrate, creating small depressions and survive by grazing on chemosynthetic bacteria that grow on the hydrate surface. Around the edges, streams of methane bubbles could be seen rising up towards the surface, sometimes encased in clear tubes of hydrate. The bubbles seem to attract assemblages of fish, darting in and out of the streams of bubbling methane, as well as fields of anemones and sea stars. This footage, captured by MBARI scientists in 2011, shows a deep-sea crab mistaking the movement of a stream of methane for food. As it came in contact with the bubbles, the gas solidified, coating the crab's claws and freezing its mouthparts together, forming a milk moustache of solid hydrate. At around 3,000 meters below sea level, also in the Gulf of Mexico, scientists discovered that vast areas of the sea floor were covered with swathes of asphalt. These asphalt seeps formed when petroleum deposits deep beneath the sea floor leaked out into the water. Lighter components rose up towards the surface and left behind denser hydrocarbons that solidified on the seabed. The result is an underwater landscape that resembles a cooled lava field. But despite seeming inhospitable, a unique community of organisms has been found living on and around the asphalt, exhibiting a new kind of cold seep habitat that remains poorly understood. In 2014, a sonar showed a cluster of structures at a depth of 1,900 meters, also in the Gulf of Mexico, with a large size indicative of a sunken wreck. When explorers from NOAA approached the site with their ROV, they stumbled upon an enormous formation, splayed out over the seabed like a flower. Later dubbed a tar lily, this was discovered to be an extrusion of asphalt. The thick, gooey hydrocarbon mass had been squeezed out from deep reservoirs in rope-like formations that bent and flowed into petal shapes, becoming hard and brittle over time. More volatile hydrocarbons dissolved, so the petals shrunk. Cracks formed, and the lily provided a hard substrate that bacteria could colonize, using the oil for primary production and transforming this extrusion into a localized chemosynthetic paradise. Anemones and corals anchor themselves on the ledges, while tube worms are wedged among the many fractures. Another process, salt diapyrism, occurs when salt flats are buried beneath other types of sediment. The salt layer is more buoyant, so it pushes its way to the surface, forming diapyrs or vertical intrusions through the overlying sediment, like salt domes and pillars. Some of the salt dissolves and flows into the diapyrs to form a lake of dense anoxic hypersaline water called a brine pool. This can be 5 times saltier than normal seawater, and it's the presence of dissolved methane in the brine that means these surreal pools often coincide with cold seep activity, allowing for chemosynthetic life to thrive. But what makes brine pools unique among cold seep environments is the zonation of the life found here. Due to the toxic nature of the brine itself, animals are limited to inhabiting just the shores of these unusual lakes. The mussel beds form a 5-meter wide ring that encircles the lake. Dwelling any closer to the brine will result in toxic shock, while living further away will starve the endosymbiotic bacteria living in their gills of the necessary compounds for chemosynthesis. The insular nature of cold seeps is similar to hydrothermal vents. They can be considered islands of abundance on the sea floor, isolated from one another in patches dotted along the continental margins. But they are also transitory, existing only briefly, with the seepage of any one site not lasting forever. To understand how the activity of cold seeps ends, we need to take another look at the process of methane oxidation within the sediments. As a byproduct of the reaction that forms hydrogen sulfide for chemosynthesis, bicarbonate ions are released. The bicarbonate ions react with calcium in seawater to create calcium carbonate in the form of biogenic rock. This explains the origins of carbonate reefs, towering rock chimneys, and spires that protrude from the sea floor at cold seeps, supporting assemblages of life and microbial reefs for a brief period, before eventually blocking the seepage altogether. The size of carbonate reefs in some regions of the Atlantic indicates that persistent seepage may have been taking place for an estimated 15,000 years. This self-destructive process may give rise to a pattern of ecological succession at certain cold seeps, beginning with the arrival of bacteria that aggregate into mats. During this initial stage, colonies of mussels form near the seep, along with their associated fauna. Carbonate outcrops begin to form, attracting tube worms which settle and live alongside the mussels. Once seepage is blocked, the mussel beds are starved. But tubeworm meadows live on a little while longer due to their ability to burrow down and tap into the sulfide flux directly. When the carbonate cap grows too large for even tubeworms to access the sulfides, all that remains is a lifeless rocky outcrop. But there may be another stage to this succession, as the die-off of tubeworms clears the way for colonization by stony corals. The corals, along with other sessile animals, make use of these outcrops as vital attachment points amidst the soft muds of the abyssal plain. The deep-sea coral gardens shown here are formed around structures that may well have once been sites of chemosynthetic activity in the form of cold seeps, centuries prior. In conclusion, cold seeps are an unusual collection of deep-sea habitats that show off the ability of life to make the most of an energy source in the most challenging of environments. From carpets of asphalt seeping from ancient hydrocarbon deposits, to explosive mud volcanoes and toxic lakes of brine, these regions push the limits of adaptation in the depths. But they also bring to light the importance of some deep-sea communities in helping to regulate our climate through providing a benthic filter for potent greenhouse gases like methane. We've taken a look at the two main examples of chemosynthetic oases, hydrothermal vents and cold seeps, to explore how life has adapted to survive here. But on the deep sea floor, food fall events have also been known to create temporary sites of partial chemosynthesis. In particular, the carcasses of whales or the remains of sunken wood host uniquely specialized assemblages of life. Let's dive in and take a closer look. Sometimes, the degradation of large food falls at the bottom of the ocean can create partially chemosynthetic environments. In the case of sunken whale carcasses, the supply of organic material supports an ecological succession of communities over time. During the first stage, vibrant assemblages of mobile scavengers gather out of the depths and strip the bones of all flesh in a matter of months. The enrichment opportunist stage follows, during which invertebrates colonize the bones and make the most of any remaining organic material that enriches the surrounding sediments. But it's the third stage, called the sulfophilic stage, when the carcass begins to support chemosynthetic life. This is due to whale bones being incredibly rich in lipids. After bone-eating Osedax worms begin to colonize and burrow down into the skeleton, anaerobic bacteria are able to get into the core to exploit the lipids. As they break these down, they produce sulfide as a byproduct, which seeps out and can support bacterial mats of chemosynthetic microbes that carpet the whale bones. The result is a temporary localized chemosynthetic environment, able to support a community of animals surviving not on flesh, but on the energy released by the microbes. We find grazers like amphipods and suspension feeders like tube worms blooming out of the surrounding sediment. But of the organisms that participate in this stage of succession, very few species are shared with hydrothermal vents and cold seeps. Because the chemosynthetic oases at whale falls are relatively short-lived, animals here may represent ancestral species belonging to the lineages of specialized vent and seep inhabitants. Thus, whale falls may serve as ecological stepping stones that once drove the evolution of life to such conditions. With around 1,600 new whale carcasses settling on the sea floor each year, and with each one lasting several decades, these islands of abundance are fairly common. The distance between carcasses may only be tens of kilometers, so it's conceivable that whale falls may provide an evolutionary interface between non-chemosynthetic seafloor scavengers and the highly specialized animals that appear well suited to life at vents and seeps. This is not true, however, of other types of food falls. While the high bone lipid content of whales makes their carcasses unique, most other carcasses are too small to support such complex communities. These mackerel, attached to an ROV and sent to the sea floor, were devoured in less than a day. This jellyfish, consisting of soft gelatinous flesh, was consumed entirely in a matter of hours. Other large vertebrates like this devil ray, observed at 1.2 kilometers deep off the coast of Angola, appear to be less appetizing. This was the first time a natural ray food fall had ever been documented, and yet despite being covered with more than 50 eel pouts, considerably more flesh endured than what we would expect of a carcass this large. The cartilage that makes up the skeleton is too thin for bone worms and bacteria to colonize. The sandpaper-like skin is too tough for the jaws of many scavengers, and the high levels of ammonia found within the flesh of sharks and rays makes them an unpalatable meal. Even the carrion of much larger elasmobranchs like this whale shark is too much of a challenge for most animals. It's for this reason that whales are considered keystone species, providing vital and unique services to the ecosystem in both life and death. But perhaps less well documented than the communities at Whale Falls are the creatures that appear to rely entirely on wood instead. Deep beneath the ocean surface, familiar but unexpected features can be found resting against the sea floor. When trees become uprooted by storms or ships capsize at sea, losing their buoyancy as the pressure of the ocean forces out any air trapped within, bits of wood sink to the ocean floor, where they create fleeting oases of life. The scarcity of food in parts of the deep ocean creates an environment where very little goes to waste. The animal and microbial life that dwells down here has become incredibly resourceful, able to make the most of even unexpected resources. So it comes as no surprise that the deep ocean hosts complex biological communities that are adapted to thrive on this sunken wood. They're called woodfalls, and they're able to support these biological hotspots by providing both a concentrated source of nutrients and a solid surface that sessile animals can anchor to. Colonies of peculiar bivalves encrust the surface of the wood. Belonging to the genus Xylophaga and growing no longer than an inch, these bivalves are woodfall specialists. They are endemic to these regions, not found in the surrounding sediments or indeed at any other site of chemosynthetic primary production on the sea floor. This is because, in order to consume the solid fibrous wood, they have had to specialize, evolving a number of traits that not many species possess. A ridged, beak-like shell is used to bore into the wood, while a large muscular foot extends from the shell and is used for leverage. They behave like living chisels. The bivalves ingest the fragments they break off, but even now the wood is tricky to digest without help. The polymers cellulose and lignin which stiffen wood are indigestible to all but some fungi and bacteria. Thus, Xylophaga host endosymbiotic bacteria within their gills that do the hard work of digesting the wood for them. The boring way of life is similar to that adopted by another species of bivalve, the inaccurately named giant shipworm. Unlike Xylophaga, these can reach a meter in length, but like their smaller cousins, they use their shell to bore through wood. Squat lobsters of the species Munidopsis andamanica instead opt for the outer layers. Rather than boring, the squat lobsters have developed spoon-like claws that tear away at the wood's surface. They, too, then employ the services of bacteria to help digest the wood. The bivalves and squat lobsters represent the astounding ability of life to make the most of any available resource. For these are deep-sea animals adapted to thrive on land plants. In many ways, these ecosystems mirror the detrital communities that form on terrestrial deadwood, where worms and beetles break down the debris and cycle the nutrients back into the ecosystem and enrich surrounding sediments. In fact, both are dominated by crustaceans. On land, woodlice burrow down into felled stumps and branches, while in the depths it's their cousins the squat lobsters that take advantage of this resource. Another similarity is that woodlice, termites, and other terrestrial detritivores must also rely on endosymbiotic bacteria to help digest the wood. But one key difference between deadwood habitats on land and out at sea can be explained by taking a closer look at the microbial life of deep-sea woodfalls. The aforementioned bacteria that are able to break down the wood do so anaerobically, forming sulfide as a byproduct. This sulfide can then be used by chemosynthetic bacteria, making woodfalls sites of partial chemosynthetic primary production similar to whale falls, and providing an alternative source of nutrition that other animals, not specially adapted to feed on wood, can exploit. This footage shows wood debris on the sea floor being converted into a sulfidic hotspot. A microbial sulfur biofilm rapidly develops on its surface, setting up the foundations of a vibrant food web that relies on these chemosynthetic microbes. Bathymodiolus mussels are one example of an animal that rely not on the wood itself, but on the microbes, feeding on the nutrients they produce. Unlike the woodfall specialists, these mussels are not endemic. In fact, they belong to the same genus that colonize other varieties of chemosynthetic oases, the towering chimneys of deep-sea hydrothermal vents, and the carbonate reefs and mounds of methane ice that form at cold seeps. Their presence here at Woodfalls indicates just how important these isolated food sources are to deep-sea biodiversity. Evidence suggests that they serve as wooden stairs for certain animals, ecological stepping stones that allow the mussels to disperse between vents and seeps, in a similar manner to whale falls. Both environments may form corridors on the sea floor that allow chemosynthetic communities to spread to new chemically similar habitats. And they do so by producing thousands of larvae, released into the ocean, where the first stage of their life cycle sees them waterborne. Currents disperse the larvae far and wide, inevitably bringing some to suitable sites of chemosynthesis, where they can settle and begin to grow. The rapid utilization and exploitation of wood by deep-sea organisms means woodfalls are often short-lived. In the case of sunken vessels, a wooden hull may last less than 100 years before it is fully decayed, meaning wrecks like this 207-year-old whaling ship in the Gulf of Mexico endure as nothing more than a patch of scattered artifacts. Seen here is part of the whaling ship's tryworks, large iron pots that were used to boil down blubber. But in March of 2022, the wreck of Ernest Shackleton's ship Endurance was found with all its wood intact, 107 years after it was lost in 1915. Situated 10,000 feet below the ocean's surface in Antarctica, it appears suspended in time. This is because woodfalls here are rare, and animals in the Southern Ocean have not adapted to use wood as a food source. With the nearest landmass, Antarctica, being devoid of any trees, there has been no pressure to do so. In addition, animals that are capable of breaking down wood are unable to migrate this far south. The sharp temperature gradient at the Antarctic polar front serves as a barrier to these animals. But despite hosting no fauna that is able to digest the wood itself, Endurance is still an oasis of life for deep-sea creatures that use it simply as a solid surface to attach to. The colonizers of Endurance are predominantly filter feeders, making use of specialized appendages to pull organic particles out of the ocean, dead animals and excrement sinking from above. Sea lilies, a type of echinoderm closely related to starfish, use hair-like structures to adopt this way of life, living alongside sea squirts, which instead trap food by cycling water in and out through tube-like siphons. A Brisingid sea star also decorated the helm, waving its arms in the water to catch debris. Anemones the size of dinner plates adorned the ship, representing a fascinating phenomenon called polar gigantism. This is the tendency of polar marine life to grow much larger than tropical counterparts, and is likely due to a combination of cold-driven low metabolic rates and high oxygen availability in the polar oceans. One unexpected hitchhiker on the Endurance was a small white crab, the first time a crab has been observed in the Weddell Sea. Similar communities to those observed at Endurance tend to dominate metal shipwrecks in other parts of the ocean, including many that endure from the Second World War. The lack of wood rules out any possibility of partial chemosynthesis, but nonetheless their rusting hulls are utilized by corals, anemones, and goose barnacles, along with other filter feeders. Fish and octopuses may use the wreck for shelter, while some creatures may use them for another reason altogether. Close to the sea floor, currents are slowed by friction, preventing the oxygen and food from being transported here. So not only do shipwrecks provide vital attachment points amidst the soft muds of the abyssal plain, but they also allow seafloor dwellers to reach faster, more nutrient and oxygen-rich currents. This is true of the wreck of the Titanic, dotted with long white corals reaching up into the flow of water. In conclusion, Foodfalls highlight the ways in which seemingly isolated deep-sea ecosystems are more interconnected than they seem at first look. Whale falls and woodfalls are vital stepping stones that allow opportunistic deep-sea creatures to disperse and colonize new regions and adapt to new conditions and ways of life. But they are also important islands on the sea floor for non-chemosynthetic life, with man-made wrecks creating unexpected foundations for corals, anemones, and the innumerable species that rely on them for food and shelter. Today's video is sponsored by Endel,